All right, so before we go into more discussion with notation and whatnot, I want to briefly go through some animation I found for AES 128. And that will give you an idea of what goes on in this symmetric cryptography engines. And also, what I hope is going to point out very clearly is you shouldn't bother to ever implement these algorithms yourself, right? First of all, they are tricky to implement because they have many moving parts. And second of all is auditing, security auditing and so on are very important for the implementation, not only for the algorithm itself, right? Which means you're much better off by finding some code out there and using it. There is lots of open source code with good licensing, and right. And since it's libraries, for the most part, in any case, you can probably just use them, even in a product. Okay, so let's see how this works. Control F. It doesn't quite work. Let me see if it's big enough. 1 second, I need the mouse. All right, so I'll try to explain roughly what's going on in here. If it works. I think it did not successfully went into full screen mode. Okay, this is flash animation. Okay, it finally works. All right. So, by the way, the algorithm is called Ringedale cipher because that's the name of the researcher, the security researcher that proposed it. It's now known as Advanced Encryption Standard 256. I mean, 128. There are multiple versions: 128, 196, and 256. They're all tightly related to powers of 2. Now, keep in mind that the idea for these encryption algorithms is to be able to implement them very fast. So powers of 2 are very good, perfect alignment in memory, all of these kind of things, right? So basically, the way all of them work is this. You have the plain text coming in, the cipher key coming in, and you have some encryption mechanism, and then the ciphertext pops up in here. If you take the ciphertext and you put it as the plain text, and you put the key again, or the complement of the key, depending on the algorithm, then you get the plain text. This is why they are called symmetric. In an easy way, you can derive the decryption key. And you apply the same process, which is a very big advantage. If the encryption is the same as decryption, you really need to implement only one algorithm, which is a big, big asset. OK, enter. All right, let's see how it works. Right, so the idea is you're going to take blocks out of the input. You can apply this in a stream fashion. I'm going to mention by the end of these slides how that works. But in principle, you can take a block of plain text, and the key has the same size as the block. So if the key is 128 bits, then the block is 128 bits. Okay? And the idea is to mix very thoroughly the state, but in a way that can be reversed. Mix very thoroughly the state based on the cipher key. Now, thoroughly, right, this is done in a cryptographic sense. So you're going to see that the algorithm is actually quite involved. Even the 128-bit algorithm is quite involved. Okay? All right. Obviously, all of this are basically hex notation. So this is essentially 8 bytes. Each of these little boxes is an 8-byte box. Okay. All right. Oops. That's supposed to go backwards. OK. They have a weird key combination to control it. All right. Now, the secret with the key, all of these advanced algorithms are going to have something called the key schedule. So they are going to take the key and derive other keys as they work from the basic key and keep on mixing the derived keys with the basic thing. So the strength of the algorithm comes from the fact that the key is never used in the same way throughout the algorithm, and all kinds of things will happen actually to the data. Okay? And we are going to see the operations that actually happen to the data. Okay? So let's see how the encryption process goes. Right? So this is a rough idea. You're going to start with the state, and you're going to do an initial round. Oops. Right? So the first round and the last round are always special. So in the initial round, you just do a simple add the state with a cipher key. But that's not strong at all. Because if you reuse the key, once you derive one key, you can derive everything else. This part here, which is going to be substitute bytes, shift rows, mix columns, add end round key, this is going to be repeated multiple times. Let's see how the animation goes. Right? So, oops. Right? So you see, you start this way, you go in rounds. if you don't do enough rounds, the algorithm is not going to be strong enough. I mean, this is where the security researchers come into play. And once you've done enough rounds, and the algorithm, in fact, establishes precisely how many such rounds actually have to happen, you do the final round and you're done. Okay? So the strength of the algorithm comes from the fact that this is a quite a complicated process, and it's repeated many, many times. So it produces this extremely thorough shuffling of all the data. Right? The 128 algorithm needs nine rounds. I think the number of rounds is higher for the 256. Okay, so let's see a little bit what these operations are. So literally, these are all designed to be simple operations that can be implemented both in software and in hardware. They substitute bytes, shift rows, mix columns, and add round key. Add round key is trivial, right? I mean, it's just a XOR between the two. Can be done extremely fast, right? And of course, the performance of the algorithm is going to depend on how fast you can do each such round. Okay, the hardware implementation actually can be done how? How many people took an architecture class and know about basically pipelining? You can essentially pipeline all the 9 stages, right? So as the data moves in at one end, it moves through each of the independent stages. These operations are so straightforward, it doesn't even take that many transistors to implement. I mean, I'm not talking about 1,000 transistors, but hundreds of thousands is not a big deal, right, in today's chips. Okay, good. So let's see about how the transformations work. And to a large extent, even though these transformations are simple, right, they are very powerful when combined with each other and combined into rounds. And this is the idea I want you to get. Okay, this is the principle behind all of these encryption methods. DES had much simpler kind of operations, but in essence, it's the same thing, right? So we have the S box. This is the substitution box, and AES uses the substitution table. Now, you see, why this table and not another table? This is where the security researchers come into play, right? So they cooked up a substitution table that has certain good cryptographic properties. Literally, hundreds of papers are written about these things, and are they good? Should we replace them, do other things? This is why you don't want to basically invent your own algorithm. But the way the substitution works is straightforward, right? So let's see the animation. So you take each of the individual bytes from the text, and you look them up, right? The 1, you see the 1 is this row, and the 9 is this column, and you simply replace with whatever is in the middle. Now, of course, this is going to be basically reversible. So you can't put any table in here. You want to make sure, essentially, that there is a one-to-one mapping between all the combinations to the combinations in the table, right? So you can actually reverse the process, because if 2 of them collide, you're not going to be able to know which one went to the original one. Okay. So then, basically, you just go and use the substitution table for absolutely all the entries. And this gives you one of the transformations. This is a substitution transformation. This is equivalent to replacing one letter with another letter in the alphabet, except that the alphabet now has 256 letters because it covers an entire byte, right? And this is a kind of a nice, clever way to even organize the table so you can do fast lookups. In hardware, you literally would implement a very fast. I mean, you can actually implement it even with in transistors, right? Good. You usually don't want to change that table, so that's part of the algorithm itself. All right, let's see the next stage, which is shift rows. Again, all of them are simple individually, but in combination, they produce this powerful combination. So usually the shifts, either of rows or of columns, right? So this is equivalent to the transposition. You remember I told you about the Caesar cipher, in which you take the piece of paper and you roll it around the rod, except that, of course, you want something that looks more modern than that, right? So you basically, the first row remains the same. The second row shifts by 1. The third row shifts by 2, and the third one shifts by 3. Okay, very simple transformation. But the important thing is the position of the data on rows changes. Transposition. So this is the first half of the transposition, and the other half of the transposition, it's the row version of this, to make sure that you have a more complete transposition, right? So this is a mixing column, is the same idea, right? First, you take the first column, mixing matrix, right? And this, in fact, is going to shift bits, right? So the mixing on columns is actually going to shift bits. But nevertheless, it's a very simple transformation, and you take rows of bits and you shift them. And this is why you got something that looks like garbled, but it's really not garbled. Okay, it's just a reordering of the columns. Again, why this combination is not others? A lot of people made careers out of this, right? Studying which of these transformations can be applied fast and would add to the security of the system, right? And Add round key is trivial. Basically, this is just a XOR operation, right? You take them and XOR them, right? Everybody knows what XOR is, right? 0 plus 0 is 0, 0 plus 1, 1 plus 0 is 1, and 1 plus 1 is 0. Okay. The important thing, so XOR is a reversible operation, right? But the normal addition is not, right? It's hard, you can't tell the difference between 1 plus 1 and 1 plus 0. Okay. So basically, you just repeat this. Now, it turns out that if you don't do enough rounds of AES, any of the AESs, you can actually attack the system. One round, it's actually weak. Okay? You can, well, weak relatively, right? So you can actually derive statistical properties about the data once you do only one round. But the trick is going to be to do a lot more than one round. In particular, we've seen that it does 9 rounds in the inner part of the system, right? Again, bottom line, it's very important. I mean, if you take this out of these lectures, I'm going to be happy, right? Look around, see what the standard is for these encryption algorithms. Find good implementations, use the good implementations. Do not implement your own implementations unless you're hired to only do the implementation of one of these cryptographic algorithms and nothing else. You can't really do normal programming and security programming at the same time. Okay, I mean, it just doesn't work that way, all right? Luckily, I already mentioned AES-256, which is the recommended one. It's implemented in hardware now in all the modern processors, all the modern server processors. Even if it's not implemented in hardware, you have very good libraries, open source, non-open source, anything you want, right? And all you need to do is just call them. For example, in Java, you have Java X Crypto, which we played with actually yesterday. This is how I remember the decimal points. Right? And it already implements all versions of AES. Do not use DES. Even if you see a DES implementation, do not use DES. DES is very weak. DES has a 56-bit key, and it's considered extremely weak. Triple DES, it's a freeway application of DES with 3 different keys. It's still not strong enough. The standard nowadays is AES 128 or preferably 256. It does not even slow down too much the process of encrypting and decrypting the data. You can actually encrypt and decrypt at high enough speeds to, in fact, have other bottlenecks in the system, for example, the disk. You can, for example, I'm not sure how many of you use full disk encryption or partial disk encryption or encrypted file systems. You don't even feel that they are encrypted. Right? The combination of whatever happens in hardware and whatever happens in software, it's able to bring the data from the disk, decrypt it on the fly, and place it in memory at speeds that are comparable with just reading it from the disk. Right? And even the CPU utilization doesn't even go that much higher. Now, this is why it's very important to standardize these algorithms. Right? First of all, you have many eyes that look at them and try to figure out how to break them, and if they survive for a very long time, that might suggest that they are hard to break. The second thing, you have refined implementations that are both fast and secure at the same time, right? So when it comes to security, I mean, the same reason you don't build your own lock, you go buy a lock, you should actually use a standard implementation, okay? Good. So let's switch now and start talking about the things we care about with more symbols and more things, because one is to have access to a good encryption algorithm, and another one is to have a good security protocol, right? So a protocol, it's a combination of algorithms, right, that specifies how you should exchange information in what way and who does what, so that the entire system is secure. The fact that you have very hard to break cryptography does not make the system secure, right? As we go along, I'm going to mention some possible attacks on the system. But for example, one of them is, I mean, we already got some hints about this. Like if somebody intercepts even the encrypted message and you reuse, for example, the encrypted messages, then you can capture it and play it back again, right? So replay can actually be damaging as much as, I mean, maybe not as much, but can be quite damaging, right? So if I convince you to make a financial transaction, and if I could play it again about 10 times, I could get 10 times more money from you, right? So protecting against this has nothing to do with cryptography per se. You need to establish a protocol to make the information that already got transmitted useless, right? You cannot do that without adding extra things to the protocol itself. I mean, in particular, what you want if you want, is some kind of a sequence number, and you always go up in the sequence number. And the sequence number has to be mixed up with the data or be part of the data that gets encrypted, because if it isn't, I can separate it and I can increase the sequence number and piggyback on it, right? We'll come back to other such issues as we go along. Okay, DES, it doesn't even matter. Now, let me just briefly mention this before we go into the protocols themselves. What do hashes do? Okay, and elucidate a little bit that idea with the seeds. So again, hashes, I mentioned this 3 lectures ago, right? Hashes compute some sort of a summary that presumably it's unforgeable. So the idea behind hashes is they are going to do a one-way transformation that cannot be reversed, right? So it's not so much as in symmetric cryptography, in which if you have the secret key, you can decrypt. The idea behind hashes is to do something that cannot be undone. So in particular, you want to resist the following kind of attack, right? So if you have some text, and you're going to hash it. I mean, the hash could be MD5, for example, which can be written on only 1 or 2 slides, or could be one of the more sophisticated ones, right? So if you take a document and you hash it, you're going to obtain some sort of a signature. The idea is the following. If you change a single bit in the input text, the signature has to change in a significant way. Not in 1 or 2 bits, because if it changes only in a small portion, you can basically manipulate it until you get something better, right? So the standard for this summaries, for this hashes is a bit change in the input has to change at least half the bits in the hash, statistically, on average, okay? And also, because this is much smaller, in this case it's 128 bits, I think, right? Well, how big is it? Yeah, I think the padded message is a multiple of this, but in the end, the signature itself is quite small, only 128, right? Or maybe it's 512, but it's still not enough, right? So because this message is much smaller anyway than the text you're trying to, in fact, sign, right? Then definitely this process is irreversible, right? But you want to make sure not only that the process is irreversible, you want to make sure that you have a very hard time matching the signature, because you can mount the following kind of attack. So security, it's about attacks, really. It's about things you can do to protect against various kind of attacks. So the attack we are trying to prevent against is trying to forge what the original was here. So here is the intent with the hash functions. For example, I have an open source product, and I want to put it out. I want to put the source code out. Or I even have a binary product, and I want to put the binary product out. I want to make sure that I put some sort of a guarantee that this is really down to the last bit what I put out. And people cannot take the open source, modify the source code, for example, to inject Trojan horses or something like that, and then publish that as my source. In order to do that, what I'm going to do is not only make available the open source code. It doesn't matter what you put in it, right? Because ultimately you can go and edit it with various kind of tools. But I'm going to put this kind of a signature, and I'm going to put the signature in multiple places, right? To make sure that it's very hard to go and forge the signature. So then, in order to verify that that's the code I put out and not even a tiny modification of it, you go, you compute the signature, and you compare it with a published signature. If there is any discrepancy, you know that the code has been forged. Maybe mistakenly so, maybe maliciously so, but nevertheless has been changed. Now, for example, in Linux, when you install a package, and Red Hat does this absolutely all the time, they pull from 2 different databases the package, binary or source, and the signature. They compute the signature on the package. If there is any discrepancy, they start yelling and saying, this code is not kosher. Right? Now, in order for this scheme to work, I mean, you have multiple issues. One of them is how do you protect against people going and modifying the signature itself, but that's a different issue, let's say. But one of the basic issues is how do you make sure that you cannot play games with the original source code to match the signature? So here is the danger. You can always leave 512 bytes at the end, in which you put them in between a comment, for example, right? So that has no effect on, let's say, the source code. But you can put arbitrary text in there. So then you can mount the following attack on this kind of hash schemes. You go and you insert whatever you want to insert in the code, and then you're going to try all kinds of variants for this 512 bytes or more, whatever you think you need, and until you find a combination that in fact matches the signature. If you successfully do so, then you have compromised code with some garbage at the end that's introduced only to match the signature that now passes the test. So you have to resist this kind of attacks, right? Now, obviously, you could always go and do this and basically just try all kinds of things you can put. And 512 is probably going to be enough, right? Because that's the size of the signature. So you can always go and try to do this, but you want to make the life very difficult of anybody trying to such an attack. In particular, a good hash will force you to enumerate all possibilities in here. You have no clue how to cut down on the work. Enumerate all possibilities or almost all possibilities in order to find a combination that actually matches the hash. So breaking a hash function, in fact, means finding ways to pad so that you match the signature. It's not like normal encryption in which you're trying to find a secret key and trying to find the original message. You have the original message. You're just trying to forge the signature. So this is more in line with signatures than it is with encryption per se. Now, just as an idea, the way this hash, for example, MD5 works, right? You have a 128-bit constant, which in fact looks like an encryption key, but it's known. It's part of the algorithm, okay? Have a 128-bit constant. And this is the message you're, in fact, trying to sign. It's called digest here. It's broken into blocks, and you're going to do one block at a time and use the previous block to go in a circle to compute the overall signature. So the signature basically keeps on, so whatever transformation we have for MD5 keeps on getting applied to a combination between what we had previously combined in the state with a new block in the state. We can apply AES-256 in the same way, right? So you remember in the animation I had, I started with some state, right? And a key. Well, there are versions of these algorithms in which you simply can use the key that actually got modified or even the state that got modified as an input to the new stages of the encryption algorithm. Pretty much like what's actually happening in here. So what's crucial, though, for any kind of hash function application, and this significantly strengthens the algorithm, is not to break things into blocks and independently independently compute hashes for the blocks, or for the encryption, independently encrypt the blocks. If you do so, the algorithm is weaker. AES-256 is still strong enough, even if you just get independent blocks encrypted with the same key, to be still quite sturdy, right? But the larger the block in which you do the chaining, the stronger the algorithm. The ultimate strength, for example, in AES-256 comes if you take, for example, a gigabyte file and you chain all of it through the encryption algorithm. The same thing happens for the hash. And anyway, ultimately, you want to have a single value for the hash because the signature is supposed to be small. Very large signatures are unwieldy, and they are a problem in themselves. Okay? And this is basically the actual specification for the rounds in MD5. Almost all of these algorithms run in rounds, right? So even for every block, you do some sort of a nonlinear transformation. Linear transformations are easily reversible transformations, right? For example, those substitutions that were happening in AES-256 or shifting between columns, those are nonlinear transformations. The XOR, it's a linear transformation. The linear transformations are useless. If you chain linear transformations, you can express all of them as a single linear transformation, right? So the strength of a chaining of linear transformations is the same as applying the linear transformation only once. Okay. All right. Now, I don't even want to go through the details. They cook this kind of stuff up mostly to be able to implement it easily on modern computers. Now, keep in mind that MD5 is considered to be weak right now. The new standard is SHA-1, which is considered moderately good, and SHA-256. Now, SHA-256 shares a lot of technology with AES-256, namely uses the same kind of scrambling algorithm with a fixed encryption key. Okay? So the technology used for SHA-256 borrows from AES-256, so a good implementation for one, you can derive it and you do a good implementation for the other one. And the block size for this is actually going to be 256. Now, there is something I should have mentioned before, because it's one of the core pillars of cryptography. And to some extent, is the standard by which everything can be measured. So one fundamental question in cryptography is there such a thing as an unbreakable, perfect encryption method? Okay? And it turns out that there is such a thing. It just happens to be very inconvenient. But I mean, ultimately, if you don't need to do this encryption too often, you have to remember that's by far the best way to do it. Okay? Namely, imagine that I have access to a source of true random numbers, and I can produce lots of such random numbers. I could, in fact, produce, let's say, a DVD worth of random numbers. And simply, when you want to send me a message, you take another portion of the, I duplicate it. I have a copy, you have a copy, we keep it in vaults, nobody can intercept it. Then, whenever I want to send a message, I take my message and simply store it with this infinitely long key, well, or at least 4 gigabytes worth of long key. It turns out that this encryption method in which the key, every bit in the key is used exactly once, it's theoretically provably that it's unbreakable, because there's nothing you can possibly exploit if indeed the key has been derived with a random number generator. But of course, the big problem is I have to duplicate it and transport it to 2 different sites. To some extent, this is what Germans used in the Second World War, right? That the daily key, the British never broke the daily key because it was, in fact, a random key. So literally, they decided on a string of random numbers. I don't know how they did it, right? Because if humans do it, it's not really random. And simply copied them under a lot of secrecy and give a copy of the book to basically all the commanders or something like that, right? Unless you steal that book, there is no way to derive what's inside because it's, in fact, a sequence of random numbers. Okay? So you could do combinations of things like this, right? So for example, you could say, I mean, a really, really nasty way to deal with these things would be, let's get such a book, for example, and use portions, 256-bit portions of this book that we shared for every single message. So when I send another message, I get another 256 bits from it, and then I use for the whole message AES 256. This is going to be an extraordinarily good encryption method because you're only encrypting with the same key possibly a relatively short message. If that's the case, it's a nightmare to attack in any way, shape, or form, even if you have some sort of an attack, because the message itself could be too short even for a statistical attack, right? So don't dismiss this kind of old school kind of solutions, right? That sometimes might actually be the right thing. Now, of course, the key is how do you generate a large amount of random numbers? And I talked about this before. You can buy now cards that have a physical process, right? It's quantum tunneling or something like that, which we know it's random. Well, we know from quantum mechanics that it's random, right? Pseudo-randomness is not good enough by any stretch of imagination. If you use a pseudo-random number generator, that's what you would attack, the pseudo-random number generator, okay? Good. All right, now that I said that, that's basically the ideal, the standard to measure everything by, right? The ideal key. All right. Now, let's talk about some protocols. So again, encryption is encryption, but the question is how do you get some kind of exchange of messages? So at the end, you can say something about who knows what and who could have mounted what attack on the entire scheme, right? So I have to remember the name of the bad guy. So usually the good guys are Alice and Bob. What? Eve, right. So we have Alice, Bob, Eve, okay? Usually, Alice and Bob are the nice guys, and they're trying to talk to each other. Eve is trying to eavesdrop and mess around with things. So a security protocols, the consideration behind a security protocol is how can we prevent Eve from perpetrating various kind of attacks on the system? Remember when I told you where you put the power meter and you measure the power and you get the key? Well, that's a very interesting kind of attack, right? So Eve, the sky's the limit for what Eve can do, right? But we still want to consider this kind of things. Okay? Now, all right, so let's see how authentication can actually work if Alice and Bob are sharing some sort of a key. Now, all the time, and this is, okay, so let me backpedal a little bit and mention another thing that's very important. You can find very good implementations of cryptographic algorithms, and you should definitely use them. All your effort has to go in properly using cryptography and possibly published such protocols to have a tight implementation. So just the fact that you use cryptography is not good enough. So the worry we have now is, how do we get these messages around? One constant problem we are going to have is key distribution. We need to talk about that separately. So in this protocol, we assume that A and B, Alice and Bob, share a key. It's this KAB. Okay? How did they get the key in the first place? That's more the purview of key distribution, which is a hard problem in itself and very tricky. Because you see, it doesn't matter how strong your cryptography algorithm is. It doesn't matter how tight this protocol is. If I find another way to get the key, then that's what I'm going to attack. I'm going to attack the key distribution because it's presumably much easier than the actual security protocol. But nevertheless, let's assume for at least a few minutes that they have a secret key, K and B. Now, the trick is going to be the following. So they have to start talking to each other. How are they going to convince themselves that they talk to the right person at the other end? Right? So this is about authentication, not about sending a secret message. You see, if I share a key with you, I can put something in I can take a message, encrypt it with a key, and send it to you. And if the cryptographic algorithm is strong enough, you're the only one reading it. But that still doesn't mean I know who you are. Also, authentication, it's all about ensuring that the person you talk to at the other end is who you think they are. So this protocol, right, it's an attempt to ensure that even without, assume that Alice and Bob talk through kind of a binary line, so there's no way to tell by the voice or other things who they are, right? So how does Alice know it's talking to Bob and Bob knows it's talking to Alice? They have a shared key. Now, notice they cannot use the key as some sort of a password, because once they do, Eve is going to eavesdrop and know the password. So how can you authenticate without ever sharing the password when you have one of these secret keys? And this is what this protocol is all about. Okay? So the protocol could actually go in the following way. Alice announces to Bob, I am Alice. Eve eavesdrops this and says, Alice is talking to Bob. Fine, no problem. Okay? Now, Bob is going to respond, right? And R is going to be some sort of a challenge. Okay? So A, it's an identity. R, it's a challenge. A challenge means I send it to you, and you have to give it to me back in the format I expect. I'm going to check that it is what I want it to be, and if it's not, I know you lied. Okay? So this initiates the protocol. Bob sends a challenge. Alice gets the challenge and takes the challenge and encrypts it with this private key, KAB. Now, presumably, if the cryptographic system is strong enough, nobody can possibly forge this message itself. Because if you don't know the encryption key, you cannot apply the encryption mechanism to the challenge to get the encrypted version. Okay? Now, once Bob is getting the encrypted version, KAB, applied to R and B, it's going to decrypt it with its version of the key. If indeed it finds the challenge right, it verified that Alice has the key, KAB. So this protocol, it's all about Bob making sure that Alice has the key, and Alice making sure that Bob has the key, right? Now, of course, some of it has to go in clear text because they have to initiate the protocol somehow, right? And hence this part, right? I want to talk to you, challenge accepted, as in I encrypted, verified. Now, once Bob verified that Alice, right? So, in parallel with Alice sending the challenge encrypted so Bob can verify that this is indeed Alice, Alice is going to send its own challenge to verify that this is Bob. Because at this point, Bob is sure that it's talking to Alice, but not Alice that is talking to Bob. So Alice sends its own challenge. Bob replies with the encryption version of the challenge. It comes here. Alice can verify that it's talking to Bob. Under an ideal situation with ideal cryptographic system that cannot be attacked. So if you cannot attack this and this is in fact a good protocol that ensures both that Alice knows it's talking to Bob and Bob is talking to Alice. This is called mutual authentication. Okay? Usually it's preferable to do mutual authentication. For example, even when you do things on the web, it would be nice if they make sure I am who I am, and I make sure that's the web server I'm supposed to talk to, otherwise it's some called phishing. Okay? Right? Now, the problem with this authentication is it requires key distribution on a massive scale if you have many people that can talk to many people. So think about it. If you have, for example, 1 million people that potentially want to talk to 1 million other people, I mean, ideal situation would be if literally I can pick up something like a phone book and communicate with some person and make sure that the person I'm talking to is the correct person. Okay? It's almost as if I verify their ID. Okay? So this happens all the time, right? You want to ensure that you're talking to whoever you think you're talking to. But if that's the case, you have 1 million by 1 million. The number of keys is 10 to the 12 that actually have to be shared in the system, and everybody must store 10 to the 6 keys. I mean, forget about the storing. The storing is not such a big problem. It's how would you even communicate to distribute that keys, and especially how would you communicate in secrecy to distribute a key, right? So this, from the point of view of the protocol, once you have the key, this is tight, and it's provably tight. The trouble is, it's not particularly practical, okay? This is why, right? I'm sorry. This is an optimized version of it. Yeah. So before we talk about that, right? So you can, in fact, send A and the challenge at the same time, right? And then send replies, right? So with larger messages, which cost only a little bit more than not as large messages, you can do it with 3 messages. This is just a point, right? I'm going to come back to the other one. You send A and R of A, the challenge. Then Bob can immediately send back the encrypted version to verify that indeed Alice is Alice, right? Encrypt the challenge and send its own challenge, and you just request the reply back. It's important to cut down on the number of messages, right? Okay. All right, so what I'm getting to, and I'm going to get to that in a few seconds, is what you would like to do is have an algorithm that has complexity that's not squared in the number of participants, but is linear in the number of participants. And we're going to do that through some sort of authentication server. Okay? We're going to come back to it in a second. This is an example of an attack. Okay? It should be Eve there, but in this case, we actually have Chuck. Right? So this particular attack is called a reflection attack. Right? So let's see how this might actually work, and let's see if the previous protocol could possibly resist this. So the idea is that Chuck is trying to convince Bob he is, in fact, Alice. Right? So here's the way the Chuck is going to work. Chuck doesn't have the secret key, because if it has the secret key, he's Alice. Again, we assume that only Alice has the secret key. A big problem in itself. So Chuck is going to say, I'm Alice, and here is my challenge. It has to send the challenge, otherwise it looks suspicious, right? Bob is playing around, and this is the first session, and says, OK, I encrypted your challenge to verify that I'm indeed Bob, and here is my challenge. Now, you might think that, oh, my God, Chuck cannot decrypt this message, but Chuck couldn't care less to decrypt this message, because he's not particularly interested whether his challenge is correctly encoded by Bob. He's trying to attack the system. He's reasonably convinced that he's talking to Bob, right? So it's going to do basically nothing here. But now it has to convince Bob he's Alice, right? The game he's going to play is, right, you see, he got the challenge here. The game he's playing is, he sends now, I'm Alice, but sends the challenge that this Bob sent himself in the hope that Bob won't notice and will, in fact, send him the encrypted version of the challenge, which is what Alice was supposed to answer, right? If Bob does so if Bob does not verify that the challenge from the other side is its own challenge, it will, by mistake, send the correct encrypted version of AB to Bob, to Chuck. Once Chuck gets this, it can actually correctly reply to this message. Now, so the assumption here is that, 1, Bob is willing to run multiple protocols at the same time. In particular, communicate with Alice twice, right? The second one is that Bob, it's not going to check that somehow, mistakenly, the other side has the same challenge, right? So this is the kind of things that could be done in order to perpetrate a perfectly good protocol otherwise, right? So then what do you do? Well, it's not so easy, right? In whatever implementation you have of this protocol, you have to check that the challenge is not the same challenge. Yes?
This only works if you have symmetric encryption.
Well, so everything I say in these slides is only symmetric encryption. Otherwise, we use the tildes and we use the pluses and the minuses. The moment you see keys that look like this, KA plus or KA minus, this is the public key cryptography asymmetric. The moment you see KAB, this is symmetric. Yes, this only works for symmetric. Now, keep in mind that asymmetric is far less efficient, and we're going to come back to that. Okay? It's important to understand that there are solutions for problems both with symmetric keys and with asymmetric keys, and sometimes it's advantageous to use one versus the other. Okay? So it's important to know the thing. Yes, this protocol itself, it's only with symmetric keys. And asymmetric keys, it's a completely different ball game. And in fact, the protocol simplifies as long as you can go ahead and do the computation with the asymmetric keys. Okay? So you understand what's happening? Chuck is going to fool Bob into encrypting its own challenge because the challenge was sent in a clear text. So lessons to take out of this. Challenges in clear text are not particularly good in the first place, right? But it's not clear that they are avoidable. But definitely allowing somebody else to have your own challenge can fool you into providing the secret that it's used to actually verify the system. Now, this is only one of the attacks. The security literature is full of all kinds of attacks like this. This is why you don't want to implement this middleware, these protocols yourself, right? Because even after 20 years, they still discovered attacks in security systems in which in weird scenarios you could fool somebody else in doing things. There are all kinds of things like timing attacks and whatnot, okay?
Shouldn't Bob realize that?
No, but again, what does realize mean? Bob is not a person. Bob is an algorithm. If you don't write code that says, hey, Bob, check for these conditions, then Bob doesn't realize anything. This is the point, right?
No, but isn't that starting of the second session before the first session actually got completed?
No. I never said that that has to be the case. And there is a big amount of value in running in parallel sessions. Right? I mean, who says you should only talk with one? But again, look. When you write the code, so this is one of the things that's important to realize. When you write the code, you're not thinking in terms of these attacks. You just write the code and you say, the code looks beautiful, it's nice, right? Then you say, hey, let's do actors, and actors can run in parallel, and I could do this thing. So remember, it takes a long time for these messages to go in the round trips, right? So you coded everything very nicely. You did not consider at all the question whether they can run in parallel or not, and you simply let them run in parallel. Most of the programs you're going to write, because of the asynchronicity of the system, will in fact run in parallel, because otherwise you have abysmal system performance. So you see, you might start with a protocol that does not run in parallel. It's horrible because it gets blocked until it gets the message, and you say, hey, simple optimization, let's make it run in parallel. By doing so, you introduce the possibility for a reflection attack, right? So the point I'm trying to make is use libraries to do these things, because things get very subtle. Especially when you do optimizations, you open yourself up to attacks, right? So attacks are about things that you would think shouldn't happen, but in a very subtle way, you can make them happen. And this, look, it's a very tricky business. I don't know if you heard. They, again, had some kind of a hacker conference, right? And of course, all the, for example, web browser manufacturers are very proud of how secure their web browser is, right? And again, in something like an hour, they broke both Chrome and Internet Explorer. So what I'm trying to say is, when it comes to attacks, especially people that are interested in perpetrating attacks, right? Anything goes, and things can get very, very subtle. And even if you're very careful, things get broken into, let alone if you do your own implementation, right? And remember, everything is software. Right? So there are no rules. If you fool it into doing something, you fooled it into doing something. Right? All right. Now, what do you do to at least solve this problem? You have too many keys. Okay? Now, to a large extent, this is a solution that's old school solution that's based on symmetric cryptography. And solutions like this are at the core of Kerberos, right, which is the authentication system in X11, right, the Windows system. And it is used on most Unix systems. Okay? And basically, Kerberos is used when you use a password to actually log into a system, okay, at least in a normal way. So the idea is basically the following, that you're going to have some sort of a key distribution center. And you establish a secret key, but with the distribution center, not with the other party. And somehow the distribution center is going to be involved into the protocol. So you have now 3 parties into the protocol, Alice, the key distribution center, and the Bob. And the protocol is going to ensure that Alice can make sure it talks to the Bob, but when it only has a secret key with a key distribution center. The key distribution center keeps the key secret. Okay? So you're going to be able to ensure that you have some sort of, so you need to do some authentication between Alice and the key distribution center, Bob and key distribution center, right? How would you put this together? Right? This is only a beginning of a protocol. We are going to see that it gets more and more complicated in order to protect against various kind of attacks. Okay, so let's see how things might actually work. So Alice initiates the whole process by saying, I'm Alice, I want to talk to Bob, and sends the message to the key distribution center. The key distribution center is basically going to do the following thing. It's going to invent a key, a communication key between Alice and Bob. It's in fact a session key. It's this KAB. So KAB was a secret key before that Alice and Bob agreed on. In this case, the key distribution center uses some sort of a secure random number generator. If it's not secure, you can attack the random number generator to invent a key, right? Now, of course, it can't send the key in the clear to Alice because Eve or Chuck are going to intercept the message and know what the key is and just wait for the other things. Okay? Now, keep in mind, these attacks are not necessarily easy to perform. But even if they are just possible, it's bad enough, and people can actually exploit them. Okay? Good. Now, in order to convey this key to Alice, it's actually going to encrypt it with the secret key between Alice and key distribution center. Alice has only one such key, which is derived usually from the password that Alice has. Okay? Now, presumably, unless you have the key between Alice, shared by Alice and the key distribution center, you cannot possibly get the key, the actual communication key. At the same time, the key distribution center can send a message to Bob and say, Alice wants to talk to you, and here is the session key to talk to Alice. The moment that actually happened, Alice can contact directly Bob, right, and use the secret key. Now, you see, Alice doesn't need to authenticate anymore Bob beyond this point. The reason is, this key is used only once for this session, and if you want, the authentication with respect to who am I talking to is ensured by the key itself, because the key is not going to be reused. Because the key gets reused multiple times, you want to make sure that again and again and again you respond to some sort of a challenge. Okay? Right? Now this is right. So this is another version of the algorithm in which, I mean, a problem here is Alice contacts the key distribution center contacts Bob, but would be nicer if Alice could contact directly Bob and present some sort of a certificate to say, I am Alice, and I want to talk to you through this secret key. Okay? That simplifies the algorithm from the key distribution center point of view and puts more pressure on the clients, which is OK, because they don't do as much communication. So the way this protocol could work is, again, you say, I'm Alice, I want to talk to Bob. Key distribution center now replies not only with your version of the key. Of course, this has to be tagged in the message to know who's who. It sends you the secret key encoded with a key between Alice and the distribution center, but it also sends you Bob's portion. Okay? And it's going to encrypt Bob's portion, the same key encrypted with Bob's key. Now, Alice knows what's inside, but nevertheless, it can't use this. Right? But Alice is going to send then a message and say, I'm Alice, and here is your portion of the key. Here is your ticket. This ticket is going to allow Bob to derive the session key and then use the encryption to continue the communication. Okay? Now, the problem at the end of this round is Bob doesn't know for sure that this is Alice. Because what you could do, especially under this step, you see, if the key distribution center contacts Bob, Bob can make sure that it's the key distribution center contacting it, because otherwise this message could not have been encrypted with the correct key. But in this case, right, you can put any garbled message in here. Bob doesn't know what the key was in the first place. Applies its own secret key, it still gets some binary message. Right? If there is nothing in the key, and you should never put such things in the key to indicate this is a valid key, the Bob would think, OK, fine, so that looks like a good encryption key, and starts talking to somebody who's in fact not Alice. Okay? So then the question is, fine, so how do you add elements to the protocol that make sure not only that they find what the session key is, but that Bob makes sure this is indeed Alice? So the details don't matter so much, but what I want you to understand is there are ways to pack more things into messages, add more keys, and add more encryptions. All of them potentially could have problems. There are known attacks against them. There are known fixes for them. And again, this is a good justification for, in fact, using libraries that do this, using middleware that do this, and don't implement this at home. So for example, Kerberos, even after 20 years, it still had vulnerabilities that they actually were discovered and fixed. If an algorithm used on billions of machines, essentially, still has vulnerabilities after tens of years, that's a good indication that you should never bother to implement this on your own. Okay? This is why it's important, by the way, to patch your system. Patching the system quite often patches, in fact, the security protocols. This is, for example, what Chrome does quite often, or the other ones do quite often. Well, there are many other ways to attack a system, so that can itself be exploited, right? So this new version of the algorithm, right, it kind of works like this. And in this way, it's hard to get things out unless you have the right key, right? And this, remember, in order to ensure the other party is who they claim they are, you could put challenges and expect challenges. I'm going to come back to this a little bit later. The challenges are crucial. You pick a random number, and you ask the other party is guess what the random number is. If they don't guess correctly, that means they don't have the key. Okay, this is what these challenges are all about, right? Challenge from A, and B. You contact the key distribution center. Key distribution center is going to prepare a nice message and then encrypt it with the key of Alice that it has with the distribution center to make sure nobody can extract the information. The key will contain both the challenge that Alice put in. And by the way, in that way, you make sure that the distribution center is who they claim they are, because you could hijack the connection to the distribution center. B, the identity of B, the shared key, KAB, and the message for B. When Alice gets this message, it's able to decrypt this, verify the challenge that verifies the key distribution center. Also knows it's B it's communicating with, so it can match the message. It knows what the secret key is, so it can eventually communicate with B. And this is the message for B. It's going to now take this portion of the message for B and continue the protocol with Bob to convince now Bob that Bob is talking to Alice. Right? So what's going to send to Bob is going to use the secret key that's in fact in this message and make another challenge to Bob and send the original message that it actually got from the key distribution center. Bob has the decryption method for this. From this, it finds the identity of Alice, and it finds the secret key and can actually decrypt this message in order to find the challenge. Now, this is a challenge that it has to send back to Alice. Now, the trick is, and this is where there is a subtle change in the protocol strengthens significantly the protocol. Namely, what Bob sends back is encrypted version of the challenge -1 and another challenge of its own. And Alice sends back the challenge Bob sent -1. Now, why the -1? Because this protects against situations in which you did not actually decrypt the message. So you see, if you can do mathematical operations correctly, that means you actually decrypted the message. So it doesn't matter that's -1 here. Any mathematical operation would work, right? You can prove that you decrypted the message by providing mathematical operation and sending the slightly modified challenge back. Because otherwise, you could just record the message and somehow do some fooling and do something to play it back. Okay? Again, security researchers analyze this kind of protocols to death, and then in subsequent papers propose attacks. How do you resist attacks? All those kind of things. And you see just how complicated it can actually get. And it's not even yet the full Kerberos protocol, okay, which is even more complicated than this, to protect against all these crazy things, right? So this is a variant of it, right? So this is a version of the protocol that protects against malicious reuse of a previously generated session key. I'm not going to go through it, but right? So even more layers of security with even more messages to protect against even more attacks. Okay? Good. So it's madness if you in fact want to use symmetric keys in order, even if you establish some sort of secret with a key distribution center. This is, by the way, at the core of the system that allows you to log in into a server. So when you log in into a server, well, logging in is different, but for example, when you use X11 and you want to make sure that this client can talk to this machine, this is the protocol that's actually used. Okay. Yes.
Mathematical function, RA2 minus 1 and RB2 minus 1. So this will be generic throughout the system, or A and B need to action them to the function itself?
Well, it doesn't quite matter. I mean, this is there just to verify the fact that you in fact decrypted this value and you could do some transformations on it. Because otherwise, it's possible to have attacks on the system in which you're just reusing the key applied to that thing, right? You see, this message is going to look very different if you do a simple operation in here, because if you have a good encryption algorithm. Remember, a good encryption algorithm will shuffle all the bits, right? So the message with RA2 minus 1 encrypted is going to look fundamentally different than the message with original RA2. And the original message has the RA2, and this one has the mathematical operation. Remember with the chuck that actually replayed something back? That attack would in fact fail if Chuck would be required to do a mathematical operation. Because Chuck, in fact, has to decrypt the message in order to correctly play this. So if I send you a challenge, but what you're sending back, it has to be the key applied to RB minus 1, then I don't need to remember the keys. That's one way to resist this kind of reflection attacks in which you record the message and play it back again, right? Because even, well, would you? Not quite clear. So look, bottom line is what I'm trying to say is these things can get very, very, very tricky. Many papers about this. It's not worth it. Just use a library, right? This is why if you need to use a protocol like this, just use Kerberos. It's available. It's implemented. It has some open source implementation. Just use that. It's not worth inventing your own. Okay, but I want you to appreciate just how interesting and complicated at the same time things can actually get. Okay, now this is something you can actually do, as long as you get the libraries to work, by the way. So getting these libraries to work is a different adventure. But let's talk about how authentication can be done using public key cryptography. I hinted to this. This is very signed, okay? Now, there is still a major problem in here. The major problem is the fact that you still need to do a large number of key exchanges. And not only a large number of key exchanges, but a big problem is the fact that the distribution center has the key. Now, why is that problematic? Because if somebody attacks the distribution center and steals the keys, you compromised everything, okay? And that's a tremendous problem, right? To a large extent, this is how the big disasters in recent history with respect to security happened, right? So the last one is Adobe. In fact, Adobe acts as a distribution center, not for the purpose of authenticated only the users and the system itself, right? But because of the way they were storing these encryption keys in their own system, a direct attack on their own systems and stealing the encrypted but with DES-free, right, which is not particularly strong, right? Then all you need to do is go and break passwords, go and break the encryption, the DES encryption, and once you found the key, you found the key for everybody else. It makes it particularly weak, actually, because the same key was used individually for each particular entry, right? How could you build some sort of a system in which even a compromise of the key distribution center would not actually reveal the keys and compromise the entire system? Right? All right, so let's see how that would work with public key cryptography. Remember, in public key cryptography, the idea is it's computationally very hard to derive the private key from the public key, right? It turns out that one way it's very easy, and it's very easy as in the public key, a simple mathematical operation on the private key gives you the public key, but reversing the operation is hard. You have to look at details about RSA or elliptic curve. And even then, it's not quite clear why is it hard, but you just have to believe me, it's hard. So this way, it's easy. The minus going into the K plus, right? Private key going into the public key, it's a simple transformation. The reverse is extremely computationally intensive, That's the assumption. Okay? Also, if you have a message and you apply the public key, decrypting this message cannot be done without the private key. So you have to somehow derive the private key from the public key before you can actually do the computation, right? So it turns out that you have some interesting symmetry in there, and that can be used to make this multi-purpose. Okay, so here are properties. Original message can be recovered by applying k minus to k plus to m, which means if you want to talk to me, you get a hold of my public key, encrypt whatever you want to tell me. I get this message and I decrypt it with k minus, and I recover the original message. But you can do also the reverse, which is possible. And this is a very interesting application. You can apply the private key to the message, and then somebody else can apply the public key. Why would you do this? This is, in fact, a digital signature. Right? Namely, this is basically the verification step, and this is the signing step. You see, if indeed this mathematical operation is correct, without the private key, you cannot possibly produce this so-called signature, right? Everybody can verify that this is indeed correct, because what you're going to do is publish what should be in here. For example, here's how you can do it. You take a document, you compute apply one of the hashes, let's say SHA-256, strong, right? You see, now we are using combinations of techniques, cryptography, hashes, and so on. I take a document, I put SHA-256 on top of it, I encrypt it then with my private key, and I'm going to send in a message both the SHA-256, which can actually be verified. So I'm going to send document plus SHA-256. This, by the way, verifies that this document has not been altered at all. Right? So I send the document, the SHA-256 plus my signature, which is in fact k minus applied to just the combination SHA-256. I don't need to encrypt the document itself. Then, on the others, to verify that is indeed I signed the document, you apply SHA-256 on the document to verify that this is the correct message, right? And then you apply k plus, which is now public, to this message to verify that you get the correct SHA-256. If you successfully do so, you verify my digital signature. Based on the strength of the algorithm, you cannot derive k minus from k plus. You now verify that I signed the algorithm. Not only that you verify that I signed the algorithm, I can't deny later that I didn't sign it, because I'm the only one that has k minus, right? So in this way, you can actually produce something called unforgeable digital signatures. I have some slides about that as well. Let me see. I keep on forgetting what it is. Right? So this is how digital signatures work. Well, this is how encryption and digital signatures could work together. I'm going to explain that in a second. Right? So let's look at this. So this is digital signatures. I want to come back to this in a second. Let's see how authentication would work with public key cryptography. Now, remember, public key cryptography means that the public key is made publicly available. Somehow has to be protected so it's not forged. Because you see, one way to have you tell me things that you shouldn't tell me is to pretend I'm, write some, again, for example, Eve. You're Bob, you think you're talking to Alice. I want to pretend that I'm Alice, but I'm actually Eve. To do so, what I could do is generate my own public-private key pair and take my public key and put it instead of Alice's public key. So somehow you have to protect against this public key swapping, right? So somebody has to certify that whatever we believe is the public key of Alice, it's indeed the public key of Alice. It's a different story, and it's similar to the key distribution in symmetric cryptography, right? But let's say we know for sure that that's the public key of Alice. Without the private key of Alice, it's not going to be possible to correctly encrypt or decrypt certain messages. So let's see how this protocol could work, right? So Alice wants to talk again to Bob. And what it's going to do is basically going to grab the public key of Bob from the phone book, or whatever it is. Grab the public key of Bob and encrypt a message that consists in, I'm Alice and this is my challenge. Okay, it's similar to the other one. Bob gets the message, decrypts it with its own private key with KB minus. Not only that, but it's going to take the public key of Alice. If you have Alice, you look it in the phone book, find the public key of Alice. Notice that they don't need to know about each other. They can only look in a reliable phone book, right? This means Alice and Bob don't have to know about each other previously. They just have to trust a certain phone book. So Bob is going to look up Alice. Everything it's sending to Alice is going to be encrypted by the public key of Alice, so presumably nobody can decrypt that. And it's going to send back the challenge. It's going to send its own challenge and a symmetric key. Why would you send a symmetric key? Well, to establish a much faster communication method. Keep in mind that public key cryptography, it's slow. It's really slow compared to symmetric key. So most of the time, the way you want to deploy public key cryptography is to establish some sort of a session key and then run on the session key, right? So perfect combination, for example, that's used all over the place right now is to use RSA or elliptic curves for the public key cryptography and AES-256 for the actual communication. All you need is some generator for this secure random numbers to generate a session key. You put the session key inside. Now, because this is encrypted with Alice's public key, only Alice can decrypt it. At the end of the protocol, Bob knows the secret communication key. Alice knows the secret communication key. And because of this back message, which now can actually use the symmetric key to encrypt the challenge that Bob sent, which means it's already faster, right? Both Alice and Bob know they are talking to each other, to the point that the identity is established by the phone book. So we still have that phone book out of which we pull the public keys, right? So we still have that issue to resolve. How do we make sure that the phone book has the public keys of the right people? Okay? Now, for example, Bob could be a web server in this circumstance, and Alice some sort of a browser. Now, let me mention something. It turns out that on using e-commerce, using using SSL, you only have half of this protocol in the sense that Alice will verify the identity of Bob, but Bob uses other means to verify the identity of Alice. And it's kind of strange because these kind of protocols were known for a very long time, and that begs the question, why is it not the case that Bob itself will use the same protocol to verify Alice, since Alice is verifying Bob? Web server versus client. Okay? So in today's web, there is this asymmetry in which, for example, SSL, HTTPS, would verify that the server is what it claims it is by looking things in essentially, or doing the equivalent of looking things up in a phone book. It doesn't even do that, and I'm going to mention in a second how the game works. But it's not the case that the server itself is going to authenticate the client based on public key cryptography, even though it's known for 30 years now that this is a very strong security. Okay? I'm going to come back to that in a second. But this protocol could work using public keys. All right. Now let's think a little bit about that phone book. And to some extent, we don't even need the phone book if we have something else. But this is called trust management and trust propagation. Right? And I mentioned this last time when I talked about VeriSign. Okay? You see, the trouble here is right? And this is a vulnerability into this protocol. How do I actually know that whoever sent me this message, anybody could have grabbed my public key, how do I know that whoever sent me the message is in fact Alice? Right? Now, well, if I have a reliable phone book, I could pull the public key, but how do I know somebody else did not replace the public key? So what you can do is use digital signatures now, which we talked about before, to have some kind of an authority to certify that this public key belongs indeed to a certain person. And this is what the certificate authorities are all about. So a certificate authority will simply certify that a certain public key belongs to a certain physical entity. And in fact, produces something called a certificate that contains who this belongs to, on what domain it can be used because it's tied to the web, right? And the signature itself. Now to sign, really you can use that SHA-256 together with the private key of the certificate authority, right? So essentially, and this is okay. So in order to get these things going, you have a tedious mechanism to get a certificate, but then a very fast process to use a certificate. So the idea is we are going to make it slow and somewhat expensive to acquire the certificate. But once you have the certificate, you don't need to contact the certification authority, and you can just go at very high speed. Okay? So the way you do this is, if you're VeriSign, you have your own public-private key pair. You wildly disseminate your public key, and you guard it with your life to make sure that nobody can actually forge your public key. Okay? You might even establish low-level protocols to make sure that you really, really contact the VeriSign server to get the public key from the server. You can cache it. Okay? That public key is very long-lived, and to a large extent, you can even hardwire it into the protocol itself. So for a protocol, for example, if you know for sure that VeriSign is actually going to sign all the packages, in the software itself that you distribute, you can say, this is the public key of VeriSign. Okay? That's the one thing that you have to guard. But beyond that, the protocol runs on its own. Okay? If you have a correct certificate from VeriSign, presumably you cached VeriSign's public key. You use the digital signature protocol to verify that this is an unforged message. The message will contain who the person is and what their public key is. Now, you see, these certificates are widely available, and you can make them available to whoever asks. So, for example, during the HTTPS protocol, right, the SSL protocol, the first step is, hey, I want to talk to you. Give me your certificate. Okay? And you just give it in clear text, no questions asked. Once you get the certificate, you're going to check that the certificate is correct. And this is why the browsers now display in various kinds of colors. Something is wrong with the certificate or not. For example, they might say, the certificate is correct, but the domain doesn't match this domain, or things like that. Or, yeah, everything is good. Or, well, this tiny, or certificate is expired, which means you didn't pay money to VeriSign, or whatever. Okay? You can put all kinds of things in the certificate, including timestamps, validity, whatnot. Okay? So, give me your certificate. I got your certificate validated. Good. Now I can talk to you. Then I'm going to use the public key in the certificate to talk to you to start sending messages, which means everything I give you, presumably, it's secret. By the way, VeriSign will, in fact, revoke your certificate if they can prove that your private key got compromised, right? So it's bad. I mean, they tell you, you get the certificate, but if you mishandle your private key, not good. By the way, the private key has to be somewhere on your server, because otherwise you're never going to be able to read what your users are sending you, right? So it's not as easy. I mean, you really need to be careful with these things, right? But VeriSign could, in fact, be used to authenticate both Bob, but presumably Alice. Now, we did not quite get there yet, right, in the sense that we have VeriSign as a certificate authority for websites. Literally, what your money buys when you go and buy an SSL certificate is you get the engineers at VeriSign making sure that you are who you are. So they're going to ask for some sort of a proof that you control a domain. For example, you say, I want a certificate for www.ufl.edu. That sounds great, right? But then they're going to say, OK, great. Prove to us you, in fact, control the domain. To prove you control the domain, you have to do a certain maneuver that cannot be done unless you control the domain. If you don't do that, they say, oops, you're not going to get the certificate. They might, in fact, even say, you know what, that's great. We need physical ID to go through this, or whatnot. Right? So what you're paying for is the human effort that goes into verifying through all kinds of ways that you're not really lying when you're getting the certificate, and you're not you're not impersonating somebody else. Because, you see, one way to attack the entire system is to pretend I'm somebody else and get something else. You can even imagine now a national registry. Some people would say that would be a disaster. But you could imagine a national registry in which presumably is going to be way better than Social Security number as an ID, right? In which everybody gets one of these public keys. They have to protect their own private version of the key. But somebody would have verified in a physical way that they are who they are. Right? All right. Still have some time. So let's talk a little bit about how could we make this run on the web. Right? As I mentioned, SSL only makes Bob run part of this protocol, but not a complete protocol with Alice. So we discussed this before. If you, in fact, use passwords and derive communication keys from passwords, even if the rest of the protocol is very tight, you're exposed to direct attacks on the server. You see, VeriSign is exposed to direct attacks on its own private key, but that's a small number to protect. It's like the Coke formula, okay? But it's very hard to protect a large database. It's probably much, much easier to protect just a very small number and to have all kinds of mechanisms to make sure that those certificates are signed in a controlled way. You only need, by the way, the private key to sign certificates, right? Okay, good. So let's analyze a little bit the situation that Adobe is in and how Adobe possibly could have done a better job. Namely, how could Adobe have avoided storing even an encrypted version of all of those passwords, which are, in fact, the secret communication keys between, we had this before, Alice Bob with the key distribution center, right? Now, notice that even if I have some key distribution center like VeriSign here, right, the key distribution center will only contain the public keys, which is great, because an attack on the key distribution center, again, signing or doing other things, right, it's guarded in a much better way. But just grabbing those public keys in a public key cryptography means nothing. They are anyway sent in clear together with the certificate. So if I have a database in which I just keep public keys, I'm not really exposed in any way. I have public keys. That's perfectly fine. So one potential thing that Adobe could have done is somehow use public key cryptography for Alice to authenticate, not only for Bob to authenticate back, the web server to authenticate back. Okay, we're going to come back to that. But let's first discuss a particular attack on hash functions and what's the best practice with hash functions right now. I mean, first of all, don't use MD5. This is the first lesson in best practice because it's too weak. But even if you use SHA-256, right, you're still exposed to attacks. I mean, attacks become harder. But when it comes to attacks, if you really want to make the life miserable for whoever tries to attack you want to make sure that they have no shortcuts in the attack process, which means they have to sweat from ground zero for every single password, okay? If they could, for example, you'll get your hands on 140 million encrypted passwords. If you could actually share a lot of the lookup tables or a lot of the other techniques that are used to speed up the process of breaking these keys among all the things that happen in the system, even though it was hard to find it, you amortize it over the course of over 100 million. Great. You make your life 140 million times easier. Okay? How do you make sure that's not happening? So one technique that's in fact used all over the place in combination with this hash functions is salting. So let's talk about salting a little bit. So it's a simple technique, but it turns out that it significantly strengthens the hash execution. So the idea in salting is the following. You're going to maintain the following table and apply the following security protocol. So I'm going to have user name in the table together with other things. Then I'm going to have the hash, and then I'm going to have the salt. And the idea is, for each user, you're going to pick a different salt, and you're going to combine the salt with the password to produce the hash. Okay? So in order to get the message that you apply the hash to, you get the password and the salt. And the key idea is that you're going to use a different salt for a different user. Now, the salt is stored in clear in the database. To verify that the user has the correct password, remember this process is irreversible, you can only verify. To verify that the user has the correct password, you take the password typed, you combine it with the salt according to how you should combine them, and then hash the result. Okay? So it's not clear at all why this is stronger than just applying the SHA directly to the password. It is stronger because it does not allow you to save work among different passwords. In fact, the password that the user uses is a combination of a random part, which is known, and the actual password that the user used. And that, in fact, it's equivalent to a larger password, right? Without the salt, lookup tables can be used, and the work can actually be used across all the 140 million. If you want to only find the one password, there is no saving if you use the salt. But if you want to crack 140, there is a tremendous amount of saving, because building partial knowledge is not going to help at all when you move from one password to another if you have a salt. So right now, best practices, if you want to use this kind of password-based authentication on a website, is to use something like SHA-1 up to SHA-256 plus a salt, store hash salt, and the rest of the credentials in the table to verify. Now, an interesting question is the following. Is it possible to do good authentication based on what we've seen today in the class? Is it possible to do good authentication but to never have the password even traversing at all to the server? Okay? So a big vulnerability here is, at least while in transit, the password is in the clear. Now you can use OpenSSL for the communication in between, let's say, or whatnot, but it's still the password the user has to be in the clear in memory of the program that has to do the decryption, right? So potentially by eavesdropping on the same machine, if you attack it, you could at least see those passwords in flight. Could we, in fact, authenticate without any password crossing? And the answer is basically in that picture. As long as we somehow established a public-private key pair with the private part staying only on Alice's machine. So let me explain a scheme that, in fact, we want to use in the thing we are actually building. And it already requires a little bit of headaches with how you establish initially the key, some key distribution for that public key. But once you have it, then presumably, I hope, things are going to be much nicer. So here's what we could do. Now, it's not necessarily easy to apply for something as large as Adobe, but definitely can be applied, for example, and it is applied by OpenSSL, OpenSSH, for example, when you have hundreds of users and an admin that actually has to approve every single account. So I'm going to have here, let me even talk in terms of a browser and a web server, but Alice is going to be the browser and Bob is going to be the web server. So I'm going to have the browser here. And this is Alice, and the server, web server, this is going to be basically Bob. Okay, so I'm going to play that game. So in order to, somehow I have to start. Let me tell you how it could run in the middle. So the way it could run in the middle is, in the web browser, and we have now technologies, by the way, in the web browser to have something called local storage. Okay, local storage basically means you're allowed to keep things in files. They're not wiped out from one session to another. And it's pinned down and verified, security basically ensured by the Chrome or whatever other browser through its own mechanisms. But you can, in fact, keep local information. And for example, all of them are key value stores, right? So you can put some kind of a keyword and it gives you a value, but the value can be a complex JSON object. So you're going to keep some sort of an information there, right, that will allow you to avoid exchanging passwords. Now, you still want to protect things by passwords, because if things are in the clear, even in the browser, presumably somebody can attack your browser and easily pick it up. But suppose somehow I generated a KA+ and a KA- in the browser. I can do that, for example, the first time when I'm trying to authenticate this browser connecting to this server. Now, once I've done this, and this is essentially key generation, I can essentially send the public key to the web server. That's perfectly secure because it's the public key. Public key can be manipulated in any way, shape, or form. Okay? Now, this private key, it's crucial for me to correctly authenticate myself, because I'm going to use an authentication protocol similar to that. I'm going to protect it by some kind of a password. So I'm going to apply a symmetric version of the key and store it in the local storage, right? But the important thing to understand is this information, it's only stored locally. It never leaves on the server, which means if you want to attack and find my private key, presumably you cannot derive it from the private key, you have to directly attack my machine. It's not enough to grab all of them from the server, because this information never leaves the browser. It's in the browser. Only this information leaves the browser. Presumably, if you do so, even weaker passwords would suffice. You just want to protect against casual breaking in, right? Your aunt uses your computer and knows that you use local storage and plays games, right? All right? Good. Now, here's how the communication can happen. Now, on top of this, you already have something like SSL, so you can actually authenticate that the web server is whatever the web server is. So that's not an issue, and the web browser already do this in the right way. So once you convince the web server to place this public key in there, right, then the web server can make sure you are who you are with a very simple protocol, which is just a subpart of what's in there. the protocol can be, I'm going to create a challenge, right? It's equivalent to RB, right? So the web server says, OK, so you pretend that you are Alice. No problem. I'm going to create a challenge. You take the challenge and you encrypt it with KA+, which you have in the clear there. You can even post it on the website. And you send the challenge. When the challenge arrives here, right, the challenge plus some other information to know what you sent, right? A challenge arrives here. For example, what you could do, and this would be reasonably secure, when you log in into the website only once, and you could run this protocol, this challenge, for example, every 10 minutes. When you log into the, when you first go onto the website, you look in the local storage, you find this combination, you say, hey, type the password never leaves the browser. Type the password, decrypt this, and put this in memory. When the challenge arrives, you use KA- to decrypt the challenge and to send it back. Now, you're doing all of this for a secure communication, so the issue of whether I'm talking to Bob and not somebody else, it's completely resolved, and I don't need to bundle up me certifying that Bob is Bob with this protocol. This is only the authentication part, right? Now, it might seem wasteful. It really isn't, because you want to use as much as possible established protocols, right? So I have a secure communication channel for OpenSSL that makes sure this is Bob. I'm just trying to establish that this is Alice. Okay? So you send the challenge back together with some other information. On this side, you basically say, hey, I had in memory the challenge. You keep the challenge in memory for 1 minute. You don't reply in a minute, poof, you're gone, right? Remember, this is generated on the fly and thrown away. You respond with the correct challenge, you're good. You don't respond with the correct challenge, you're not good. End of story. Okay? Major advantage is password never crossed the boundary. This guy never knew either this part or this part. It all stayed here. Okay? The only problem with this protocol is how do you initially make sure that Alice is Alice when you put the key in? It's similar to the VeriSign problem is how do you make sure that's the case? So at least the way I'm thinking about this is I want to have sure three-factor authentication to ensure Alice is Alice, but beyond that, we are all good. Now, there is another major advantage. So, for example, think about this as being given a physical key. Okay? Suppose I use multiple browsers on multiple computers. Now, one is to go through the annoying mechanisms to establish to the Bob that I am Alice, and another one is to do it for every single browser they use. Okay? So an interesting question would be, once I establish that I'm Alice, could I come up with a simple mechanism to propagate this right to another machine? And the answer turns out to be yes, because all I need is to propagate this. So we are thinking about implementing a very simple thing in which you take this encrypted private key and you export it as a file in whatever format you want, and then you allow people to put it on a USB stick and then take it with them and put it in another browser or put it in a file system. As long as it's actually the encrypted version, it's reasonably secure. Now, you still have to guard it. You don't want to put it on servers and whatnot. The important thing is this information never is sent to the server. Most people will attack the server, most hackers. You see, it's very expensive to attack individual clients. You don't know who's who, right? If you tell, for example, Adobe that we went after 1,000 of your 140 million clients and painstakingly kind of somehow broke their local security, Adobe is going to say, yeah, whatever. Right? But if you say, we stole all your passwords and we know where they are for 140, then it's a completely different ballgame. So you don't have foolproof security here. You just have a much harder time in doing massive damage to a website. Right? So if you take this, you put it on a USB stick, you put it in another browser, another thing, if you know the password, you can actually now, you propagated the rights. Because the web server is not going to establish necessarily the identity. Depends on how you design the protocol. It's going to establish the identity based on IP address and other things which are unreliable in the first place. It's going to do it based on, do you have knowledge of the secret key? And if you do some protection of this, you're good. Now, this is similar, for example, to how SSH works to allow you to log in without a password. Right? Very similar. And in the end, it's not a particularly complicated security protocol. Right? So how does that work? Once I log in into the server, if I place my public key in a special file, that will allow me, since it's allowed by SSH, if you check on the option, that will allow me, by just responding to challenges, to verify that I am who I am. So on my, it's a very similar story. So this is my, my desktop, and this is my server. Right? In the server, in the file system, and it ends, it turns out that I even know the file names. Okay, so there is a directory .ssh, and in .ssh you can put not known host, authorized keys. Right? So in the directory .ssh, there is a file, or you can create the file, authorized keys. It must have the right rights. If you put here public keys, then in fact, you can log in without a password, because you have the private key here. It turns out that it's also somewhere in this directory, so you have private. Right? So during the communication, you say, hey, I want to use the public key authentication. Then the server says, OK, great, challenge. You use the private key to decrypt. You send the challenge back. OK, good, you're in. Because ultimately, the server just has to say, yes, you are who you claim you are, and then I let you in, or no, you're not, and kill the connection. OK? Now, I would strongly suggest if you ever set up a server and you set up access for the users, that you do this. Instead of asking people, OK, decide what your password is and do the password or not, you say, no, no, no. Go on your desktop, generate a public-private key pair, and give me the public key through some means that will, in fact, allow me to certify you. For example, I talk to you on the phone, you immediately send me the email. That probably means that, and it comes from your email address or whatever. That's where the two-factor, three-factor authentication comes into play. You take then that public key and you simply place it into this file. This is, for example, the way we set up accounts for users. We automatically generate a really complicated password. We create the account with a really complicated password, because that's what Linux wants. We don't even keep the password, except for the root of the system. Great. And you can even say you cannot log in for a password. And any user that wants to certify another machine, we say, yeah, generate a pair. And then I'm going to let one by one, I'm going to give you access to this pair. Revocation is also easy. You just deactivate the entries in authorized keys, and the person cannot log in anymore. Right? And then you don't depend on, oh, somebody knows or doesn't know the password, what it is and what it isn't. And the system is, in fact, very secure, because most attacks on an SSH server are going to be password attacks. Right? People trying to log in and trying simple passwords, admin with a simple password and one not, right? You'd be surprised just how many such attacks happen all the time if you put a machine in the wild. And this way you can sleep at night, right? You say, hey, I mean, first of all, I don't know the password myself because it was just a very complicated throwaway kind of password, and we use public key, and unless you have the private key, you have no chance to go through with the protocol. And we know that because SSH had very few vulnerabilities in the last few years. Okay. So if they break into mine, they probably can break into everything else. But, right? Security by making yourself small in the big sea of people. That's not a bad kind of security, by the way. Right? Very practical. Because once you have this, it's actually ultimate convenience. It's the same thing here. Once a day, for example, you can force people to put the key again, but you can actually do this challenge every time the connection goes down, or even every 10 minutes just for the kicks of it, right? So then the system becomes very, very hard to exploit. Even if on portions they break something, it's going to be hard to actually keep the session open, right? And do things on my behalf, okay? Again, why they don't use something like this? Well, I can tell you why. Because all the pieces of the puzzle have been put there in the major browsers only in the last about 1 year, 2 years. Once we successfully switched to the new Internet Explorer, new Chrome, and new Firefox, maybe in about 1 or 2 years' time, namely they become popular enough. I mean, you have to get to a point where you say, you don't have the right browser, you don't get access to the website. Before we start doing that, so, by the way, part of the problem, maybe this is a way for me to vent, but part of the problem is Internet Explorer 6 to 8. They are not even that popular anymore. They are only about 10% of the market right now. Most of the mess up on the web right now is due to the fact that you have to be backwards compatible with Internet Explorer 6 to 8. Right? Especially Internet Explorer 6, it's not compatible with anything. And most of the websites at the time were designed for Internet Explorer 6 and not the rest of the web. And they have their own set of rules. And it's extremely expensive when you do web development to be compatible with this kind of Internet Explorers. Right? Not to mention that people that have Internet Explorer 6 tend not to upgrade. We know this because, I mean, you literally have to wait for the machines to die. Chrome, it's self-updating, right? If you got Internet Explorer 9, it's self-updating. They invented the self-updating only in a later version, right? If you're stuck in here, it's like frozen in time, right? None of this is possible for Internet Explorer 6 to 8. None of it. I mean, you can't do any of this stuff, right? But you could require people to say, hey, go get a real browser. Chrome works even on very old Windows machines. So there is really no justification for using such an old thing, right? So in case you're tempted, this is going to be the thing you hate the most. So in everything we build, we simply ban Internet Explorer 6 to 8. Actually, we need Internet Explorer 11 for some of the gizmos, but 9 to 10, it's OK for the normal stuff. And we simply detect 6 to 8 and say, no, can't do, right? It's just, all right. Good. So we talked about digital signatures. Now, you can also make sure that the message is private and it's signed. Yes?
Instead of that is the case, why can't we develop a software or something to just perform that simple action of authentication and download it from Adobe software?
Yeah, so here's a right. So it turns out that so there is a solution for Internet Explorer 6 to 8. It's called Flash. Okay. Because anything that was worth anything was done in Flash, and Flash is in fact supported by those guys, and you can write in an older version of Flash line, and it's kind of going to work. The trouble is, then your code looks like a Frankenstein. You want to use HTML5-like facilities, like the cute things like this, local storage and whatnot, and it works on the vast majority of the browser, but for some of them you have to use Flash to do something else. Or you have to switch back to Flash, but Flash is dying. You see, when you develop software, any exception kills you. Right? This is why developing for one platform, it's so much nicer and you get a higher quality product than developing across the board for all the compatible platforms. So all of that is possible, but can drive you mad as a developer, literally. Okay? And since the market share is going down significantly, the question is why not just force those people to do the right thing? Because you still don't know if it's secure. It's almost the same issue as, oh yeah, you can do it, but then you have to invent your own security protocols. We know, for example, that local storage is guarded in a secure way by the newer browsers, which means, so here is a danger. If the local storage, so if instead of using local storage, you're going to use some kind of a local file or something, it's either inconvenient or you have a big security hole. Because you want to make sure only when you come to my website, you can do this. Because one way to attack it is with something equivalent to a phishing attack. I lure you on another website. And then I run some JavaScript on that website that will look up in the local storage, grab this encrypted key, and then in the back start to break them. Okay? Chrome does not allow this. None of the modern browsers will allow this because this local storage is available only, unless you have a vulnerability, only when you are on a specific domain. It's tied to the domain. They verify the domain. If you have certificates, it's hard at least, right? I mean, you would have to break the security of Chrome or Firefox or the new Internet Explorer to do this, right? So this is building upon the strength of existing systems and trying as much as possible to capitalize on that, because otherwise you just introduce another big security hole. Even if you do it in Flash, you trick it in Flash to do it in Internet Explorer, you have to store it in a normal file. Flash can actually access normal files, but then so could other people that run their own version of the Flash that accesses the normal file. And here goes your encrypted file, right? That's one reason not to do it. OK. So it's not as easy, especially when it comes to security. Things that look OK, in fact, have vulnerabilities and can be exploited. OK, I'm not going to go through this. We talked about this, and this secure replication server, this is another issue. I want to wrap this up next Thursday. So we're going to discuss some of the high-level issues, how we can do things. But basically, you can start thinking about using encryption to protect the data. And the moment you protect the data, you want to make sure even the data replication is done under secure conditions, so on and so forth, right? I mean, things can basically start from there. This is, for example, I mean, I'm going to let you do this. Look at the details about Kerberos, which itself is kind of a complicated protocol. Okay? So some high-level issues I'm going to talk about next time, and then we wrap this up. Now, understand that this is only the beginning. Okay? What I'm trying to do is whet your appetite to think in the right way about security. There is no such thing as teaching complete security anything. Okay? just think before you use and don't take anything for granted and stick as much as possible with existing mechanisms. Presumably they are used by many people, and bigger companies like Google have a big interest in keeping them secure, right? It's this story versus write your own Flash. You can write your own anything, but you're never going to fill the security holes, okay? And then you're successful, and then it's exactly what happened with Adobe. At some point, DAS3 was good enough. Hey, we have good security. They just never upgraded it. And then you have this big debacle, and then lawsuits and stuff, right? You should see what happens with Adobe once the lawyers get on top of their head, right, with stuff. So as a small company, you just might as well close the shop if that happens to you, or a medium-sized company. All right, so I'll see you Thursday, and we talk about some of these umbrella things, and then wrap this up because we need to talk about other things, okay? Quiz only in this weekend about all the security issues.